Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It is a pleasure to have Peyman Mohassel with us this morning. Peyman is a student at UC Davis, as you can see from the slide, finishing up his PhD, working with Matt Franklin. Peyman has done a lot of work in the area of secure multi-party computation, an area that I'm especially interested in because I did work in this area years ago when we thought that this was an interesting area, but not a lot of people seem to care about it very much. It wasn't used in practice at all. And part of the reason it wasn't used in practice seems to have been that we were focusing more on sort of look at this great thing that could be done, but yeah, it wasn't very practical. Peyman and some of his colleagues have brought this to practice. The area is now getting a lot of attention and interest because of largely his work and the work of a few others who have made this area more efficient, introduced real practical, efficient protocols, and broadened the set of functions that could be computed efficiently. And today, Peyman is going to tell us in particular about his work in this area on protocols for secure linear algebra. So, thank you, Peyman.
Thank you. So can everybody hear me? Yeah? Okay. Well, thanks for the nice introduction. I mean, the work I've done is just part of a much larger work that people have done more recently on making secure computation more practical. So I'm going to today talk a little bit about some of the directions I've pursued in my research for doing that, and then go into a little bit more detail about specifically secure linear algebra protocols. And this is work jointly done by many co-authors, including my advisor, Matt Franklin. Okay, so the overview first, I will give some introduction about secure computation and what is the setting, the problem we are considering. Then I'll mention the three directions that specifically I've been focusing on for designing more efficient protocols, and then go into a little bit more detail about secure linear algebra. Okay, so the conventional setting you have for secure distributed computing is you have multiple parties, P1 through Pn, each of them with their own private inputs, x1 through xn, and they want to compute a function of their inputs while still keeping their inputs private. So at a high level, the security requirement is keeping your inputs private while doing something useful with them distributedly. And also the classic example is the millionaire's problem, where you have two parties, each with their own private inputs, which is how much money they have, and they want to compute, basically, they want to find out who is richer. So the output they want to learn is whether x is greater than y, but they don't want to, for example, reveal exactly how much they own. So that's the classic example. But there are more unconventional settings as well where secure multi-party computation get used. Just one example is where there is an asymmetry between the participant in the protocol. So, for example, you often have clients which have their own private inputs, but they don't necessarily do the computation on their own inputs, but instead they send it to a set of servers that they don't necessarily trust, and these servers will do the computation for them. So the issue here is basically how we can do this without having to trust the servers for doing the computation. And examples of this in real world, you see online auctions. Mixnets are a scenario like this where parties send their inputs to be mixed. And more recently, cloud computing, for example, is another service where people send their data and do computation. Okay, so why look at security here in this setting? I mean, the obvious reason is the data is sensitive. You often work doing computation on data, which is patient's health information, ISPs, private networks data, and so data is sensitive. But probably more important is that it's often shared between many parties. So not a single entity has all the data to do the computation on. And in other cases, you have systems that are just distributed by nature, such as peer-to-peer networks or wireless networks. So there's no way around doing a distributed computing in some sense. And there's other scenarios where just clients are limited in the resources they have, so they have to outsource this computation to a set of servers, and they don't always trust those servers to do the right thing. And so the examples, as I mentioned previously, cloud computing, scientific computing, etc. And the way it's probably done these days is usually you just trust the servers with your data, all your data, and they do the computation for you. But maybe in future that's something you can provide additional privacy to the clients in some way. Okay, so the adversarial model I will be looking at in this work is where you have an adversary who can corrupt a fraction of the participants in the protocol. And usually there's two main cases, either less than half of the parties or more than half of the parties. These are the two main cases. And then you also make assumption about the nature of the adversary. You either have an adversary that is malicious, which means he can do anything he wants. He can deviate from the protocol in an arbitrary way, or a semi-honest adversary who will follow the steps of the protocol but will try to learn more information based on the messages he receives throughout the protocol. So for example, for the case of semi-honest adversaries, you can imagine a software that is not necessarily malicious, but someone can go and look at the logs of the software and try to learn additional information. So there's some settings where semi-honest adversaries makes sense, but other settings where you have to consider malicious adversaries. And I mean, the final variation is basically the assumption you make about the computational power of the adversary, whether it's unbounded, so you don't assume any bounds, or whether based on some computational assumption you assume that adversary is limited in some way. So these are the variations we consider in our definitions. And then the definition is usually, and the definitions we use for our construction is a simulation-based definition where you have a real world where the real protocol takes place between the parties, and an ideal world where parties send their inputs to a trusted party who will compute the output and sends it to the corresponding participants. So the idea is that the ideal world is very limits the adversary quite a bit. So there is very few things that the adversary can do because most of the functionality is performed by the trusted party. So, and the goal is to basically say that we design a protocol that makes the real world behave in the same way that the ideal world does. So the best an adversary can do would be what he can do in the ideal world. So basically say for any adversary in the real world, there is a simulator in the ideal world so that what they output is indistinguishable in some sense. So that's kind of the high level idea of the security definitions we consider. It won't show up in the rest of the talk, but it's good just to know what are the security definitions we are working with. Okay, so there's many important and classic results in secure multi-party computation. You can basically compute any function securely using existing techniques, but they're not being used in practice. And I mean, you don't see them being implemented and used very often. And I mean, one main reason is inefficiency. And I guess with inefficiency, the three main metrics that I have been looking at is one, round complexity, where round means number of rounds that parties exchange messages between each other. And then you have communication complexity, which is the number of bits communicated between the parties throughout the protocol, and obviously the local computation. And so some of these protocols don't achieve the best efficiencies in that sense. But I mean, probably also important is that the main focus in a lot of the work is on the asymptotic efficiency of the protocol. So the constant factors are sometimes very large, or in other cases, the crypto, for example, primitives that are being used are very expensive to implement. But I mean, besides the inefficiency factor, there is also the problem that some of these protocols have really complicated descriptions, or there is no real easy to understand description for developers to work with. And some of them, in fact, are more of an existence result rather than trying to describe the protocol. So that's also another issue that I guess limits the usage of these protocols in practice. Okay, so I mean, there's some exceptions where protocols have been implemented and been used. So one good example is the Fair Play Secure Function Evaluation System, where in that work, the authors basically compile any function or program into a circuit and then use general techniques for securely computing any circuit based on Yau's garbled circuit protocol, which is a classic result. And this is actually implemented in software. But so this is only efficient when the circuit being computed is small. So as the circuit gets larger, it tends to become impractical. And even for some simple functionalities, this compiler will lead to relatively large results. So it's to some extent limited. There's also some recent work in a project done in Denmark where they have looked at performing bit contract auctions privately. So this is actually in practice being implemented where by designing basic secure multi-party protocols for basic functionalities such as addition, multiplication, etc. So there is some developments in really actually implementing the protocols, but they're still narrow in their scope and how practical they're. Okay, so I've been following 3 directions. I will first talk about basically the first one, which is designing protocols for specific functions, looking at the specific problems and try to design more efficient protocols. And then towards the end of the talk, I will talk a little bit about also the other 2 directions that I have been following. Okay, so now protocols for a specific problem. So I mean, when you look at a specific problem, you can consider the specific nature of the problem you're looking at. And that means you can customize the crypto primitives that exist or kind of design new ones even sometimes for your problem. And probably even more importantly, you can choose the algorithms you use, and you almost many times you end up basically designing new algorithms for the protocol you want. So these are all the advantages you have that you don't have in a general construction for getting better efficiency. So I've been looking at several specific problems such as doing operations on sets, stable matching, which is used to rank medical students. More recently, I've been looking at some genomic computation functionalities. And what I'm going to talk a little bit more today is secure linear algebra. So let me just jump into the work I've done on secure linear algebra now. So, but to just get an idea of what the problem we're solving here is. So one example is solving distributed linear systems. So you have multiple parties, each of them with their own set of linear constraints on a set of variables, x, for example. So you can imagine, so the x is, the set of variables is common between the parties, but the set of constraints are different. Okay, so each party might have some set of constraint on the set of variables. And their goal is to find out whether there is a solution to that set of constraints or not. So basically, the parties want to find a solution to this linear system of equation that combines their constraints. Okay? So, but they don't want to reveal their set of constraints to each other, and they just want to find a random solution, uniformly random solution to this linear system if possible, without revealing additional information. So that's one example. I mean, and the example and the applications that you can consider for secure computation is obviously doing scientific computing And you often see that this scientific computing is outsourced to servers because it's expensive. For example, in my university, mostly the data is sent to the computation is basically outsourced to national labs to do the computation for them. But at this point, usually you trust whoever that entity is that does the computation for you. So you can see that maybe change. And for example, when you study properties of networks, shared networks, for example, ISP networks, there's many the properties of the network can be actually expressed as linear algebra. For example, one example is, for example, if you have having a perfect matching in a graph can easily be related to determinant of the adjacency matrix. So there is a lot of connection between properties of a graph and linear algebra. So you can use those also in those scenarios. Okay, so the problem we have is basically doing secure linear algebra, meaning either solving a linear system, computing the rank of a matrix or determinant of a matrix, etc. So just basic linear algebra functionalities that can come up in practice. And the setting we have is that we have a matrix or a linear system that is shared between multiple parties. So in the multi-party setting, we assume that it's shared using a linear secret sharing scheme. But you can imagine that you can go from other types of sharing in practice to a linear secret sharing scheme. And in the two-party setting, we assume that this is just additively shared. So we also have two variations in the security, in the computational power, where in the multi-party setting, we look at information theoretic security. In the two-party setting, we are achieving computational security. And we assume that the adversary can be malicious, so it can behave arbitrarily and disobey the prescription of the protocol. Okay, so what are some of the existing works here? We have the general construction of yaws. And so using the best algorithms for linear algebra, you get O of n to the omega communication and constant rounds. But if you really want to think of a practical protocol, it's closer to cubic n. And this is kind of an important thing that we want to really have something that you can implement and use. So, and there's also improvements, for example, by Naur, by Nissim and Weinreb, where they try to kind of bring down the communication complexity to of n squared, which is almost optimal because that's the input size you have. They kind of lose a little bit on the round complexity. And again, this is also related to that omega function. So the practical round complexity they can get is linear in n. So there's a trade-off basically between round and communication complexity. And the security they achieve is only against Semihonest adversaries. In the multi-party setting and information theoretic setting, things are even less efficient. So the best work, best construction by Kramer et al. Basically has n to the 4 communication, which is relatively large for large matrices. Okay, so in our work, basically we design constant round protocols that roughly achieve O of n squared communication. So more exactly, you get O of s rounds and O of s n to the 2 plus 1 over s. So for any constant s. So by choosing what s is, you get a trade-off between round complexity and communication complexity, and you can kind of get arbitrarily close to O of n squared. But I guess beyond asymptotic efficiency, we were kind of concerned with how big the constant factors are. So I've done a rough calculation. So I don't have the exact constants, but I kind of have a bound that it's less than 13, like here and here is the constant factors you would kind of be looking at. And the primitives we use are simple. In the multi-party setting, it's a linear secret sharing scheme. In the two-party setting, it's a additively homomorphic encryption scheme, both of which have efficient constructions. So avoid expensive. So just to give you an example of some kind of improvement we would get in the multi-party setting is, compared to the best work previously, if you have a 100 by 100 matrix over some field of size, some So I forgot actually when I did this calculation how big the finite field was that I was working on. But you can get a significant improvement. This is the communication complexity. So for large matrices, so the gain can be quite a bit. Okay, so we defend against malicious adversaries. So that's kind of a summary of the results. But let me go into a little bit more details on the approach. So first we reduce the linear algebra problems we're looking at all into testing singularity of a matrix. Then reduce testing singularity of a general matrix to testing singularity of this especially structured matrix, Topless matrices. And then from there, we reduce the protocol, designing a protocol for testing singularity of a matrix to doing matrix multiplication. Okay, so and finally we design a secure and efficient protocol for doing matrix multiplication. So I will start with kind of giving a protocol for designing a matrix multiplication protocol, and then go into a little bit more detail about the other steps. But that's the general framework. So let me first define what is the protocol we are looking for. So here I'm focusing on the two-party case, but the techniques actually easily generalize to the multi-party case. So I'm just avoiding that for simplicity. Most of the whole approach is the same for both cases, and also both for computational and information theory setting. So the setting here is that there are two matrices M1 and M2, and parties want to multiply these two matrices. So the matrices are shared between the two parties additively here. So Alice holds A1 and A2, and Bob holds B1 and B2, and A1 plus B1 is M1, and A2 plus B2 is M2. So that's the setting. But the parties don't learn the product matrix. What they learn is a sharing of that matrix. So what happens is Alice basically generates a random matrix C, and what Bob learns is the product matrix plus that random matrix. So in a sense, the output is also shared between the parties. And the reason for that is because you want to compose this protocol, run it multiple times throughout the bigger protocol for linear algebra, and so you don't want to reveal intermediate information about the inputs. So that's what we want to achieve. And in terms of using homomorphic encryption, it's easy to do, and efficiently. So let me quickly introduce homomorphic encryption. So homomorphic encryptions, we have a public key encryption scheme here, where the public key is known by everyone, and the secret key is held by one of the parties who can decrypt messages. And then the properties we have is, if you have encryptions of two values, it's easy to, without knowing the secret key, compute encryption of the sum of those two values. And again, for a publicly known value C and an encryption, you can compute the encryption of the product non-interactively without knowing the secret key. It's also easily generalizable to doing similar operations on vectors and matrices, again without knowing the secret key. So we have kind of these doing multiplying matrices if you know one matrix as well. So these are kind of neat operations you get from a homomorphic encryption. So considering semi-honest adversaries, so now it's not too hard to see how we can do matrix multiplication. So Bob can basically encrypt his input matrices using an encryption scheme where he generated the public key and secret key, and send that encryption to Alice. And Alice will generate a random matrix C, and what she can do is now compute, given the encrypted input from Bob, compute this encryption of Bob's final output here without having to decrypt. Okay, so for example here, so all the terms in this product will become the product of a term that is known to Alice times a matrix that she doesn't know. So it's the homomorphic properties let Alice to do this non-interactively. And so basically Alice sends that to Bob, and Bob will decrypt and learn his output. And that's it. That's the matrix multiplication protocol. And you can see that it's constant number of rounds, and the messages exchanged are 3 encrypted matrices. So you have n-squared communication between the parties. Yeah.
Yeah, maybe you can clarify. There's multiplication going on here that's not scalar, isn't there?
What do you mean? So you mean these matrices?
Yeah.
So yeah, that's the generalization of, I guess. No, so I guess, so looking at let's say, okay, so you have a matrix A1 where Alice knows, and also he knows if Bob B1, right? So let's say she wants to compute E Bob A1 B1. That's kind of her goal. So I guess looking at the matrix is, you have.
She's got A1.
She's got
clear text form.
Right, right. So that's what happens with all the terms in that product. She either knows both or at least one of them. Okay. Basically, yeah, by breaking down that multiplication to a couple of terms. Okay. So, yeah. So the main issue here is that it's only secure against semi-honest adversaries. So, for example, if Alice decides to compute something else, there is no way of detecting that from Bob. Or so there's no verification process here for parties behaving honestly. So now the idea for turning this into a protocol against with security against malicious adversaries is, first, each party will encode his input matrices using a ReedSolomon encoding. And let me explain quickly how this works. So, for example, if this is an input matrix by Alice, well, Alice will generate D random values in the field, and where D is some parameter that will be defined, and then he will where the coefficient, these are the coefficients of a polynomial, with the constant coefficient being an, and then in the encoding, basically, he will evaluate this polynomial at k different inputs, right? And she does so for every element in the input matrix. So given an input matrix, it's encoded using k different, a collection of k matrices. And here k is the security parameter. So we get error probability that is exponentially small in k at the end. So that's the choice of security parameter. So now having this encoding, so both parties will encode their inputs in this way, input matrices in this way. And now the matrix multiplication is done by performing the semi-honest protocol that I described earlier on every pair of encodings that correspond to each other between the parties. And the idea is that the final output matrix that they get, the final encoding that they get is actually an encoding of the product matrix they were looking for. ReedSolomon encoding of that matrix. Okay, so now to kind of verify honesty, what you can do is reveal a random subset of those semi-honest protocols and prove, show that your randomness and your transcripts that you did those honestly. And what happens with this opening is, first, because there's less than D of them opened, it doesn't reveal any information about the actual input matrices. But at the same time, it gives you a guarantee that there's only a small fraction of those semi-honest protocols that were done maliciously. So, which means that the encoding for the final output is a valid encoding of the final output. And then you can actually use the ReedSolomon decoding algorithm to recover the output of the matrix multiplication protocol you originally designed. So that is the high-level idea behind turning the protocol from security from semi-honest to malicious adversaries. Okay, so I'm done with this last step, basically designing secure and efficient protocol for matrix multiplication. Now I will go in a high level and describe these other steps. I won't go into much detail on them, but please feel free to ask me more detail about the actual techniques. But before I say something, I mean, just because I've been mentioning Topless matrices, just mention that there are structured matrices where all the elements on the diagonals are the same. So you really have O of n distinct elements in each matrix. So it's a very structured matrix, and that's why we can do things more efficiently than general matrices for Topless matrices. Okay, so the second step was now having a secure matrix product protocol, designing a protocol for testing singularity of a Topless matrix. So we have a secure matrix multiplication, and the techniques we use are basically, first, we need to use a formula for computing traces of powers of the Topless matrix, covert formula. And once we have those traces of the Topless matrix, we use Leverrier's lemma for getting from the traces, finding out whether the Topless matrix is singular or not, by first computing the characteristic polynomial using Leverrier's lemma and then testing the singularity. So I'm not going into much detail about it, but the idea is that both of these steps, and what is interesting about them is that they reduce to doing matrix multiplication. And the number of matrix multiplications you have to do is independent of the actual input. So it's oblivious to it, so, which is some property we need for having privacy. So the computation has to be oblivious. And in fact gives us the efficiency we are looking for. So that's kind of why this choice of these techniques instead of maybe others. So once we have protocols for testing singularity of a Topless matrix, we want to kind of extend that to general matrices. And this is actually kind of interesting because there were these techniques by Wiedemann in 1986 and then later extended by Kaltofen and Saunders and etc. that were designed for operating on sparse matrices. And so what it turns out as they are randomized algorithms. It turns out that we can actually apply them to general matrices because they have this nice property that we want to that they are kind of oblivious to the number of multiplications, matrix multiplications you have to do is oblivious to actual content of the input, and you can reduce everything to doing matrix multiplication. So it was an interesting use of the techniques that were previously only used for sparse matrices, but they're only meaningful to use for general matrices in the context of like secure linear algebra, I think. Because if there was no privacy concerns, they're not the most efficient existing protocols for example, for linear algebra. Okay, so again, that's there was just a general idea, and then actually reducing all these other problems to protocols for testing singularity of a matrix are rather standard techniques, and they don't require much. They don't increase the complexity of the protocol, and so all these important problems that can easily be reduced to testing singularity. So, for example, to give you an example, in case of a rank of a matrix, it's easy to do a simple binary search on rank of the sub matrices, for example, and find the rank. So there's techniques for doing that. But just let me quickly summarize. So this is the efficiency we get for any S, constant S. And the whole point was to reduce the protocols we want to do to a sequence of secure matrix multiplications where number of multiplications is independent of the input being used, so it's oblivious. And then designing secure protocols for matrix multiplication. And while I only talked about two-party case and computational setting, it's, the results are for both settings, and the efficiency we get are for both settings. And also I've been working with two undergraduate students at Davis trying to design the two-party protocol for two-party case to implement it, and we've kind of decided on the primitives we're going to use, but we haven't had to actually start implementing. But it's actually because the implementations for Pyre's scheme exist, all these operations over final fields, there's libraries that do that relatively efficiently, so it's not going to be hard actually to put those together, but hopefully we can do it before I graduate. Maybe I can finish. There's a lot of questions, I guess, maybe remaining, but one of the main ones is, for example, what about sparse matrices? Can you do better? Because in practice, usually you have sparse matrices and not general matrices. But one more challenging, I think, question is that these linear algebra protocols are designed for over finite fields. They work over finite fields. What about working over integers or reals, and what are the issues there? You can sometimes choose the final field to be large enough so that it fits, so you can be kind of assume you're working over integers, but that can also be inefficient, or there's stability issues. So there's a lot of questions, but they're not only restricted to linear algebra. They come up in almost anything that you do with numbers in secure computation, because you often are working over a finite field or a ring of such as or a ring, because all these encryption schemes, for example, are this way. So it's an important question, I think, for trying to apply the techniques to practice still. Okay, so now I will also mention the other two directions that I've been following. So relaxing the notions of security and also coming up with cheap techniques for strengthening the security when possible. Okay? So relaxing the security notions. Here the idea is that in practice, it's sometimes reasonable to relax the security notions, this simulation-based security notions we have, to get a more efficient protocol. So one and the goal is to get more efficient protocols, really. So one example is the covert adversaries, which are a relaxation of having a malicious adversary. This was recently introduced by Aman and Lindell. And the idea is really simple. So you have an adversary who can cheat, but there is a reasonable probability that he will get caught. So originally you would require the protocol that there is a very high probability. So 1 minus a negligible probability for them for the adversary to get caught, but you're just making this some, maybe even a constant, in depending on the scenario. And it turns out that by doing this simple relaxation, you can actually design much more efficient protocols. So we have been looking at secure general two-party and multi-party protocols in the covert adversary model and design more efficient protocols. So this relaxation seems to be successful. But I think there's so one thing I've been looking at more recently is studying what if you allow for a limited leakage of information in a protocol. So can you do things more efficient? So the goal is that, the idea is that in practice you have many protocols that already leak many information. So one example, you often test the quality of files by comparing their hashes, and obviously this leaks some information about the content of the hash of a file leaks some information about the content of the file, but not everything. So and maybe in some scenarios this is a good enough protocol for doing equality testing, but the whole point is to quantify what is the leakage here and what is exactly the security we are getting. The other example is that in the context of electronic voting and using mixed nets, there's this work by Jacobson, Rivest, Jules, and I think others. That's it. Okay, where they to verify in the verification process, they reveal some partial information about the ciphertexts that are encrypting votes. But the argument is that this leakage is in the context of electronic voting, it's insignificant and doesn't lead to much information being leaked. And they get more efficient protocols compared to the previous ones for verifying, validating the votes. So, and a more recent example is in the case of deterministic encryptions, where you don't use any randomness to encrypt. So inevitably, the ciphertext is leaking. Some information about the plaintext it's encrypting, but you can get, for example, more efficient protocols for doing search on those encryptions. So again, here is another trade-off you have with leaking some information about the plaintext, but getting some efficiency. So what I've been looking at is in the context of secure computation, how can you formally quantify the leakage in the protocol? So coming up with the formal definitions for what is the security you get? What does it mean to, for example, leak some k-bits? And then try to design protocols that meet that definition. But in general, in the context of relaxing the notions of security, I think this is at least in the secure computation field, it's in the earlier stages. So I think there is a lot to be done. For example, considering economic models for what would be a good incentive to prevent, for example, cheating, and in that sense relaxing the security definition. So I think I would be definitely interested to continue working in that area and looking at even specific protocols where certain relaxations make sense. Okay, and finally, I've been looking at like cheap techniques for strengthening the security from semi-honest adversaries to malicious adversaries. The general techniques that exist are usually using zero knowledge proofs, generic zero knowledge proofs often, and but those are very expensive and very hard to implement. So that's kind of one of the reasons where you see a lot of protocols in the semi-honest models, but not their counterparts in the malicious model. So I've been looking at, for example, in the case of Yahoo's Goblet Circuit protocol, I've been looking at techniques that improve the security from semi-honest adversaries to malicious adversaries. And more recently, I've been looking at protocols that evaluate parties' inputs at multivariate polynomials and try to get the same strengthening of the security from semi-honest to malicious adversaries without kind of losing the original efficiency you had in the semi-honest case. So I've been looking at this strengthening and there as well. So I think that is it for me, and I would be happy to answer some questions. No. Thanks.
Questions? We had some earlier, I guess. Thanks again.
Thanks.
And, good opportunity to talk to you, Victor.
Sure.